Alrighty, after some delays with Twitch and not working, finally here to get started. So today my plan is to work on adding timeouts to an event loop for database I'm building. So we'll be using IO Uring for that, and lots to figure out because I've never done this before. So this is the repo I'm in. It's called Event D. It's on my GitHub profile. Let's just go ahead and start looking at things. Let me know in the YouTube chat if music is too loud or if I need to make the text bigger or anything. So, general way this is set up is I have an IO loop here that has a tick function that on every loop it tries to handle any in-queued IO events, and if they are ready, call the callback. So you can see I have a list of continuations here, and those are basically the events that have been submitted. It's a doubly linked list. Let's go get those. So those are completions are defined in here. They're defined in here. So a continuation, continuation, not completion. Easy to get those confused. So basically what a continuation is a command, status, and then it's a internally linked list. I forget the actual name for this. It's it's built into Zig. It's a very common idiom. That is not actually accurate. I think that's an older version of Zig where these are not. Well, thank you. Let me just turn down the music then, because my mic is turned all the way up. I probably just need to talk louder too. Alright, so yeah, so continuation basically has a command, like what command it is, status, a link to any other continuations, and then a callback that should be executed when it's finished. Its status, as you can see here, is either queued, which means it hasn't been submitted to IO Uring yet, waiting, which means it has been submitted but isn't done yet, and then completed. And then basically the main file. So right now I just have a main file that all it does is open a TCP connection or a socket, and then just waits for a listener on that. You can see here, I create a new IO loop. I create just a array of continuations, just 10, set it undefined. We don't know what they are yet. Add a new, or basically pass the address of the first continuation into loop.accept, which will accept a new connection on this socket right here. This file descriptor is to a socket, and then that will except if we go look at that, you can see it all it does is call accept data and sets up the necessary items for the IO Uring call, and then enqueues the continuation, and then we just say while not done, we tick. And I guess it's worth calling out. Here's the actual completion. The callback that gets called is just a dummy thing that prints out what happened and sets done equal true, so that will exit out of this loop. We can see this in action. Let me just pull this up. build. You can see it'll just sit here and tick because it's waiting for a connection. And we can grab a connection real quick. So I have it listing at port 5678. And SOCAT is basically just a tool that lets you read and write from file descriptors. You can look at the command page for more info there. You can see that we submit that. The result status is completed. The file descriptor for the connection is 5. So you can see that it actually did open up a new file descriptor, and it's working. So what I want to do today is add a timeout to the actual event loop, so you don't have to just sit here and do this thread sleep. You see, it's basically I'm doing it sleeping for 1 second and then calling loop tick again. What you can do instead is submit a timeout with IO Uring, and then when you call into IO Uring, you can say basically wait for X number of events to complete, and you know that that is now bounded by your timeout because your timeout will complete after X milliseconds, and so you don't need to actually sleep or do any like busy waiting. So that's the goal here. And are all the volumes okay at the moment? Let me know if they're not. Then we will. Then we will get started. And it's been about 2 weeks since I've actually looked at this code, so it'll take me a second to get back into the flow of things. Cool, thank you. So first thing is if we look at our folder structure here, we have like an IO file. And this is our generic file that will then call into the operating specific implementations. So right now I'm just working on Linux. So you can see this const IO is a type, and you can have it be test IO, or it switches on the OS tag. Right now it's just Linux. You can see if we go to definition on the Linux one, you can see it has a tick function, handle complete, get CQE, log, accept, everything. So like in the accept example, we're just looking at, you can see this is the actual IO Uring call. So this is get SQE, which is get submission queue event, I think is what the E stands for. Can I select a more visually abusive theme? Sure. I'm already probably flashbanging most people with this lighter theme. Let me try to get something super obnoxious for next time. I don't know if any of you guys have seen the McDonald's theme for NeoVim, but that one's pretty great. So get SQs. So basically how IO Uring works is you have a submission queue and a completion queue, and all they are basically a piece of shared memory that you share with the kernel. When you want something done, you add an entry to the submission queue array, and the kernel will see that when you call submit, and then you, on the other side, you say copy or wait on the completion queue event, and you wait for new things to be added to it. And that's when that's in there, it's done, and you can make use of it. So, like in this example, we get the address to the submission queue that we're trying to add. So it gives us basically a pointer into the submission queue, so we can modify the memory there, so we can create our submission. And then this prep accept is the function that actually goes and arranges the memory in the way that the kernel wants it, so it knows it can do this. Takes the address of the submission queue, the file descriptor, the address length, and any flags. Right now it's just the socket that we have in our command, and then the only flag I'm passing is the close exec, And if you pass null for the address and address length, it will just kind of figure it out itself and give you what you want. The other special thing about IO is when you submit this event, you have some memory allocated for user data, and this is just a pointer. So you can basically attach any data you want to the submission event, and then you get it back when you get the completion event. In that way, you can basically attach metadata or any data you want to the event. And in this case, we are attaching the continuation itself, so that once we complete it, we have the command, the status, what's next, and the callback, importantly. So here's this accept. This is what gets called when we see the submission queue completion event. And basically, it will give us a result, which is an I32, because that's how results are modeled in kernel land. And from that, we can get the POSIX error. If you've ever looked at these, there are a bunch of just error codes that are related to numbers. So that is how we get that. And those they're always less than 0 when it's an error. So to map that to the actual number, you take the negation of it to get a positive number. And then we convert that to nice Zig error enums. You can see, like, in our result type that, I'll talk about commands in a second, but these are all most of the things that can happen when you accept and it doesn't work. And then if it is, we have a command, we have a result for the command, and we just give it the file descriptor, because that's all I'm pulling out of right now, and I think that's all we actually get. Yeah, so if the result is greater than 0, what the number is the file descriptor number. So in our example over here, it was the 5. So that's the file descriptor we got back out for the accepted connection. All right, so I guess it's probably good now to talk about the commands, because that's how I'm encapsulating a lot of the logic. So you can see here, like, we're returning like an accept result, so we know it's strongly typed that this is actually what we want. And so this is an IO file. Let's just go down to, okay, and this is one of the things I love about Zig, is you can at compile time make new types just by like calling functions. So basically so I have a enum here of commands, and I want all the commands to have a similar structure. So you can see, like, accept, close, open, read, write. So what I am doing here is calling command and passing in an actual type for the type of the data you want for the submission, and then another type for the type that you want the result to be. And you can see we return a new struct that has a field called data with the type of data t, and a result of a maybe result type. And then we also create a init function that returns the default, with the result being null and just the data being set. So if we go down to our accept example, here we go. So we have this enum, this error enum of all the different things that could break when we are calling accept. So basically how errors are handled in Zig is it's just an enum of a bunch of values. It's kind of like Rust, but the upside being that the compiler is smart enough to figure out what the enum should be if you don't specify it in most cases, maybe in all cases. And so you don't end up with these like giant ball of mud errors that you would in Rust. But the downside is you can't really attach other data to the errors like you can in Rust, but if you have your own custom implementation of the error type. So anyways, so now we set up, the accept command is command, and we have the data, and then the result is an error set of accept error or accept result. So you can see it's not just a simple type that we pass into the above function, it's actually this fallible type, and it's all strongly typed. So like accept data. So this is what it takes to set up an exception. It takes a socket for where we're listening to, the address size, and then this toCommand function, which basically translates this data into a member of the command enum above. And then the result is just a file descriptor. And this is another kind of cool thing. You can label any block comp time, and that will guarantee that it will be executed at compile time, which I think is super nifty compared to like bus macros or anything. But right here, I am asserting that the size of this overall struct is the same size as just the file descriptor. It's probably not super necessary, but it makes me feel better to know that if I ever accidentally or inadvertently add something to this struct, this will fail, because I want to keep this to just be as minimal as possible, like just basically passing around the I32, which is what the file descriptor type is. And I'm not adding any bloat or memory overhead by wrapping it in a stronger type. So that's how the commands work. So what we want to do today is, I guess, start off here, is just add a timeout error. It's going to be an error. I don't know what it will have yet, but it will be there. And then we want data. It's going to be a struct. And this is the point in time where I might get made fun of because I'm not using AI to do this, which obviously it could just, autocomplete itself, and I wouldn't have to write any of this. And then just keeping with how I have things structured above, I'm going to do and equals CMD, and then this is going to be the timeout data, and this is going to be the timeout error or a timeout result. And that's basically all there is to it. And now we have to figure out what exactly we need to pass into this. So how I do that is I search in the man pages for prep timeout, which will give us the IO Uring prep timeout docs, and see what it takes. So prepares a timeout request, submission queue entry, not event, sorry. Is a Dharma timeout specified by TS. And then the flags, modifiers. Okay, so we have a timeout absolute versus a relative one. I'm not sure which one we want to use. Boot time, real time. During timeout, E time success. So this is one that I'm keen on playing with. So normally when a timeout occurs, with the syscall timeout, you get a E-time error back, like this error. Like this is the POSIX error that gets returned, and we'd eventually have to handle. But in my case, a timeout isn't actually an error. It's just we're keeping track of like application state, so we don't really want to consider it an error. So we want to set this IO Uring timeout E time success, so that it's not actually considered an error when the timeout is thrown. And then I don't want to mess with multi-shot today. And then return value is none. Is that true if it's okay, so the res value will still be okay. So I guess even if I set this, it'll still set the error. So it will not sever dependent links as a failed request normally would. Okay, so maybe I don't mess with this today because we're not having anything depend on this, and it seems like this will still just set the error time, the e-time argument as the return value regardless. So we'll just have to handle that. And yeah, the comp time assertions are really cool. It's one of my favorite things about Zig. I don't know if I have any other good examples. I do a lot of the assert the size of this thing so that I know I'm not bloating anything. And then this is all in Tracy, which is a tracing library that I'm going to get rid of because I don't like it. Yeah, all I'm doing is mostly the asserting sizes, or that's all. Definitely all I'm doing, but it's a lot more powerful than that. Okay, so the errors that we have here are going to be it's going to be e-time, which is it's not actually an error, so I think I might want to remove it. But then there is also I don't know if you don't know if what, DJ. There's invalid inputs, I guess, for this error inval. 2 clock sources can notice specific timeout or now 6 or less than 0. Invalid. What did I do above for invalid? Did I do anything specific? Invalid argument. I mean, that makes sense. It's generic enough. So yeah, I think I want to get rid of e-time, and then so then the next one is e-fault. Uring was unable to access the data specified by TS. So I don't know what a generic way to say that is. I'll just say false. And then there's also canceled. You'll notice if you don't put commas at the end, the Zig format will collapse everything, which is kind of annoying. I like it spread out more. Okay, so that looks like basically the only things that can happen. So the timeout data, we know we'll need a timestamp, which is, I'm just gonna say any type for now because I need to figure out how to do that. I'm just gonna say void, whatever. We'll need to figure out what data type that actually is. And then any flags, which we also need to figure out. And we're gonna see if there's any built-in niceties in the library. Yeah, that's a good point, Dustin. So by error here, do you mean non-success? And is cancellation actually an error or not? I don't know. I haven't figured out error handling yet, or cancellation handling, I should say. Let's see. I'm not handling it in any other case, so there's an argument that canceled should be handled specially. I just haven't figured out actually how to handle them yet. So I guess that's a good point. We should just not handle it and cross that bridge when we get there. Because cancel is a... I guess I'm torn because in theory, you might want to have a callback that's only called when you actually cancel something, not when there's an error. So I think it probably deserves its own handling. Yeah, and for the control flow, I could definitely see something like you want to handle something differently if it's canceled, but again, like you could do that in your callback function because you get access to the error in the callback. So you could still handle cancel differently. I guess it's a question of whether you'd want to pass in just a separate function for when it's canceled, but that gets really kind of messy, I think, when you're passing function pointers around. I guess it's probably worthwhile to show like where the definition for the callback is. Let me see. Continuation. Yeah, so this is the callback. So it's a pointer, or it's a const pointer, which basically means it has to be known at runtime. I mean at compile time. Sorry. That's not true. Yeah, it's just a const pointer to a function. So like you need to know at compile time like what options there are for like what this can be. So it takes a context, which is an only opaque, which means it's just a pointer to something. You don't know what it's a pointer to. And then you get a pointer to a continuation. And your callback always returns void. Somehow I hit play on my dream on the side. I don't want that. So yes, that's what the callback looks like. And then let me go back to the dummy function so you can see how it's used. Let's see, am I just ignoring? Okay, so the context is a pointer to the IO loop, so that you have that available if, like, in your callback, you need to enqueue more things. Because in most cases, right, you don't just want to do one IO operation, you do one, and then everything it's dependent on is like more IO operations. So you get a pointer to this, and then Zig, how you do like a cast to the data type for the compiler to know what it is you have to first align it, and then you have to cast the pointer, and then you tell it its type is a pointer to an IO loop. Kind of fuzzy for me because I haven't looked in a while, but that's, I think, just how it works. So let's add our timeout here. There, and then again, Zig has an amazing compiler, so that is now using their own backend versus before it was using LLVM. So now it's even faster. So it's amazing. It's larger though, so I can actually see what it is. So we can see in the error, we're going to get some errors now that we're not handling every case of this email, which again, it's like Rust, it has exhaustive matching. So it's super nice for refactoring like this, for adding new things. You find all the places where it's going to be used. So first one's in Linux at 56. So we need to add a new one here, which is timeout. We're just going to say void here because we need to implement it, or I'm going to say unreachable, so that it panics if we try to call it until we actually implement it, and we'll come back and implement it in a little bit. And then the next one is in ios.sig, line 28. No, sorry, I'm reading it wrong. Is that the only one? Oh, there it is. You want. Cool. So same here, we need a timeout. Here. So I need to wire all these things up. I think that should be all of them. No, okay. Oh, it's because I spelled this wrong. Cool. And they do have a Zig build watch that every time you save a file and it's super fast. So I might just leave that running now. Just get rid of that. So now what I want to do is actually go down into like how we do this in Linux so that we kind of have a better idea of what the types actually are. Yeah, the watch is super fast, and there's let me see if I have it in my history. Yeah, I don't on this computer, but you can make it not output the actual binary. So all it does is actually just, run all the compile time checks and make sure like everything's good, but it won't output the binary, and that's even faster. But I don't remember what that is. Also don't know why it says watching 79 directories. That seems like an awful lot. I mean, if we looked at the file structure here, I guess, is it watching in Git too? That might be why. Zig cache. I don't know, that seems like a lot. Okay, so let's don't need that file. Don't need that file. Alright, so let's look at in our Linux file, Linux invitation. We have a bunch of file or stuff in here in tests. So I want to go to the last one, which I think is, yeah, right. So as in the function, right? I'm just gonna steal this to base it off of. So instead of right, we want this to be timeout. I might want to say set timeout, makes it more readable maybe, but that doesn't actually align with like the syscall timeout. But okay, I'll just call timeout for now. And then so generally how it works is like, unless you're actually working on like the Linux or whatever operating system implementation of IO, you should never have to touch like IO directly. You should only ever touch the IO loop. And then the IO loop has the, the more generic user-friendly functions. Is generally how I've set this up. So a timeout will take or return a submit error, which is basically when you submit to the submission queue, there is a chance it will fail because that is a fixed like array of memory, and you could have no free entries in it. So you need to be able to handle when it fails, and how I generally handle. I mean, I can just copy all of this right now. So then we get some boilerplate. So here's our first assert that we see. There's in Zig and in a lot of like lower level languages, you do a lot of asserts to make sure that your data is in the right shape and in the right state, because you really have the power at any point in the code to reach into something you're not supposed to and change values, and you're breaking a contract of the program at that point, and you should just panic. So it shouldn't be allowed. And if you build in release safe, all these assertions are kept in the code. So they do have some kind of runtime penalty. It's not a lot, but if you run in release fast, all of the asserts are stripped out, and then you don't get any of that. So the idea is kind of how much risk you're wanting to take. A lot of the like suggestions I've seen is run in release safe in like your staging environments, and then in your prod environments run and release fast. And sorry, my wife is coming in to work on Legos in the background. And then sorry, I lost my train of thought there. The so relief safe in staging, release fast, and prod. The downside is you could have things in prod that you haven't hit in staging if you don't have an accurate staging environment, in which case you're not panicking where you probably should be because your invariants have been broken. So if you know anything about Zig and databases, you probably heard of Tiger Beetle. And they run just in their prod in release safe, so that they're always checking those invariants, which is something I kind of prefer as well. But it does come with some runtime penalties, so you have to be careful about what your asserts are doing. Alright, so what we're going to do here is assert that this... Sorry. Sorry about that. So this continuation, right, has a command inside of it, which is going to be one of these variants of this enum. And we just want to make sure that whenever timeout is called, that we're asserting that this is the timeout, variant of the command. Because if it's not, something has gone horribly wrong, and we just want to panic. And the same for the status. Whenever we are getting this continuation, we should be tracking it as queued. Like if it's anything else, again, something is very bad, and we should just panic. This might seem like it contrasts with some of the things I like the parse don't validate that I'm always harping on. And in some senses it does, right? You're always checking, like you're always validating, which I don't love, but at the same time, I feel like it's a little bit safer too, because that your program will crash if something is going wrong, and you can catch that. It is odd, but I kind of reconcile it with myself that I use strong types wherever I can, and then just assert them. Let me see one of the first things I'm working on here is implementing the Postgres wire protocol. Let me see if I can find. Yeah, so what I've been doing is in all of my major structs that have like business logic have a assert invariance function that gets inlined, so there's no like overhead for it, other than more code, because it's going to get put everywhere it's called, that has all of your asserts in it. And then all you have to do is basically at the beginning of your function you call the assert invariance, and at the end of your function you also call assert invariance. And the reason why you do that, see, here's an example for like the deserialize, where I'm deserializing some, the startup message from Postgres. You assert it in the deserializer, and then at the end you also assert it, so that you haven't messed up your internal state yourself either. Which I think is actually more powerful than what we normally at work do with Rust, because in Rust we've leaned heavily into the strong typing and the parse don't validate, but what we don't actually check there is things that have access to the fields aren't doing something stupid with them. So think where you declare your new type over an integer, and instead of an integer you want it to be an ID. Things in that same module can go in and do dumb things with that, and there's nothing stopping about with the visibility of it. So that, in one sense, you get more protection there, and this is also inspired by NASA's power of 10 rules. You just whenever you get things in a function, like in the function call, the first thing you do is assert that they're what you expect, and the last thing you do is assert the state of the world is what you expect, which I think for safety critical code makes a lot of sense. And I view, databases as safety critical code because you don't know what people will be relying on them. I wouldn't necessarily recommend this for everything. So that's how I justify it to myself. It's like I would love for Zig to have better visibility modifiers on internal types, so there's less chance for something to reach in and then do something stupid. But I can also kind of understand why they haven't done that, because it's definitely not the norm for lower level language things. So back to this. So we want to grab the timeout data. Yeah, I agree. It is a weird thing, right? That there's less of a type safety thing and more of just a modeling thing, I feel, in Zig for your types. At the end of the day, it's a low level language. You can do incredibly stupid stuff with it. I could literally just take this pointer here and point it to something completely different and then cast it back, and no one would be the wiser. So I get why you can't really, be as type safe as we'd want to, in our Rust code. It's just, I guess, a trade-off of having a lot of power, I suppose. So now in data, and here, this is why it's important that we assert it here. We want to grab the timeout variant of the data and set it there. And this is how you basically access the active enum variant, is you just reach into it and grab it. And if we hadn't done this, and this wasn't the timeout variant was not the active variant, then this would panic. And so that's why I want to assert. I guess you could then argue, why is it necessary to assert when both these would panic? But I find this to be more declarative. So self here again is IO here, and IO, how we have it in here, has basically two things. It has the IO Uring, which is this implementation's built in the standard library. It has a bunch of stuff in it that makes it IO Uring a little bit easier to interact with, and then a count. So we're basically keeping track of how many things we currently have in IO that we're waiting on or need to be queued. Let me get back to where we were. Okay, so we get the submission queue event, and then we're not going to prep it right. So we want to get rid of that, but everything else is, just comment that everything else is the same, right? After we're going to do a prep a timeout, and then we're going to set our user data to our continuation, and then increase our count by 1. So let's do sqe.prep timeout. So what does this take? It takes a itself, which is the SQE. It takes a kernel time spec, which I don't know what those are, a count, and then flags. And let's go back to the man page and see if we can figure out what count is. Okay, so count. Okay, the submission queue entry is set to arm a timeout specified by TS, and with a timeout count of count completion entries. That is not super clear to me. I'm guessing, is this how many times it can fire? Let's see if count, okay, the value specified in count is the number of repeats. The request will return multiple timeout completions. The completion flag is set if more timeouts are expected. The value specified count is the number of repeats. A value of 0 Means the timeout is indefinite and can only be stopped by a removal request. Okay, still not super clear on that. So let's, I guess we'll just do some experimentation once we have it wired up. Okay, so what is kernel time spec? Let's, okay, it's a Linux.kernel time spec. So let me just go to Linux. I know I have it up here. Go to definition and look at kernel time. What is? Okay. Okay, kernel. Did I just spell kernel wrong? I guess. Time spec. Okay, so what is this? Okay, so it is a second and nanosecond thing. Okay, so how I have been handling these is if we go back to our IO loop at the top, you can, is it IO loop or is it just, sorry, no, it's just in the generic IO. Oh, sorry. So inside of the Linux one, we declare some constants. So we want to do pub const spec type equals Linux.kernel time spec. So then we have, we know what type it is. And then once we're wiring things back up now in the IO. We can now know that our time spec down here is a IO dot time spec type. That's the type that we want to pass in as our data. And it's delegated to the IO here because it will be different for every operating system. So we don't want to make it like a specific type here. We just want to delegate it down. And then the same can go for, you just pull up the, I don't need that file. Jumping back to where we are. Sorry, and I just completely lost this one. So let's just go back to there. Okay. And then and then count and flags are just U32s. So now we know that in our flag here, we're just going to do U32, and I'm not going to pass count in yet because I don't know if we actually want to do anything there. So now we can do, this is going to be data.ts. Count is just going to be 0, I guess, for now. We'll figure out if that is the right thing to do. And then here we're going to do data.flags. That's it. Now we know that we have everything we need for the prep timeout call. And then now we need to handle a timeout completion. So I'm going to steal this and do timeout result. Same thing here as timeout. Okay, so if result is less than 0, which I think we know it will be, we should get a compiler soon here. So this timeout, and then we want this to be time result, and that's going to, do we put anything in our timeout result? We didn't, it's just a struct, which is fine for now. Although we could make it void if we wanted to. I'll think about that later. So I think, which errors do we have here? So yeah, I'll just do a Let's pull up the errors here, so we know we're handling them all. Oh, and there's an unexpected error. I usually include that in everything. Don't know if that's the right thing to do or not, but at least gives me a fallback if needed. So we could do, is this right? It's a dot. Okay, so we could do a dot. What is this? Default. Just do that for a second, see if it'll compile. It will. Okay. Is it actually in the POSIX or is it just fault? I think it's just fault. Yeah, it's just fault. Okay, so yeah, it drops the E off the front. That makes sense. So if it's fault, it's that. In this case, we want error fault, which I think is what we set it. Yeah. And then we want this would be inval. Without argument. Then unexpected. All right, so we have this. So I think we want to say this is unreachable here. And then this is dot time. Okay, so timeout result, we don't need this, so we can just get rid of this. There. So that is, I think, all that we want to do. Add a comment here. Actually, here, I know a better way to do this. Oh yeah, that is a good point. The only reason why I am using an else here, Dustin, is if you look at the POSIX.e, you can see we're in Linux. This is it, and then basically you have to handle all of these. So there's, you know, a lot of them, but I know already that most of them are not relevant to what I'm doing. So that's, in general, I agree with you, but maybe it's just laziness here that I don't want to do that. I mean, in theory, I could add all these and do a unreachable next to them, and that'd be more explicit. But it's, man, I'm just being lazy. I don't want to do that. It leads also very huge files. Maybe not, because you could do. All right, so let's just look at like what this will do. Like, say I comment this out. Why is that not catching it? Oh, it's because I'm not actually calling this anywhere. So that's half the problem. Gotcha. Yeah, it's a built-in one. So our build thing isn't actually doing anything because we're not calling this function anywhere. And that's one of the gotchas, I guess, as you're doing like development work, that if you're not actually calling the function, it's not getting compiled because they won't, in the call chain, it doesn't see it, and so it doesn't do anything with it. So you basically get automatic, was it tree shaking, like in JavaScript, where you get rid of all the unused things. You just get that by default, but it can hurt you if you're not aware of it. Well, yeah, false positives. Yeah, everything's great. It's perfect. So what I was getting at though is if it's an invariant, the result will always be less than 0. Let's just assert that. Less than 0, like that, and then we just get rid of this, like that, and there, bam, no more if statement, and we are clear that we are expecting it to be less than 0. Yep, I think that is it. So let's actually try to call this and see what happens. I guess we're not quite there. We have a unreachable here. So here we want the timeout result that we just wrote with C and result. And this is the handle complete function. This is what it's called here in tick. So you can see we submit and wait for 0, which means we don't wait at all. And I still have some just random panics in here because I haven't figured out error handling yet. And then we set up some memory to copy our completed entries into. And then we copy some, maybe not any. It could be 0, but we basically see if any are ready and copy them over into our memory. And for each of those, if it doesn't actually have any user data, continue. I think what we're to do here is that this should assert this. The reason why I'm not making that change right now is because I know it works with this and I don't want to break anything in the middle of doing this, but I think we should just assert here instead of continuing, because every completion event every completion entry we are submitting should have user data, which is the pointer to the data that we want to attach to it. So then we grab the continuation from the user data and just cast it to this. And then we call handle complete, which then will switch on the command and call the different result functions. And that is it. So I think welcome to the future, DJ. It's a brave new world. I do have a warning that my bitrate is a little bit low for this stream, but I didn't want to mess with that since I already had a bunch of issues with Twitch. So I'll try to up that in the future, but maybe that's why you're delayed for some reason. I don't know. So let's see. So now, how do we call this function? So now it's time to go back in the actual IO loop and then hook this up. So we want a something similar to like the IO.read or write. Let's just go to accept. It's a simple one, and copy it. Or did we already write this? Yeah, we did. We already wrote this. I'm stupid. Oh, I'm in the wrong file. So this is just as simple as self.io.timeout. Passing in C. There we go. So that is done. And now we finally have errors because we're calling the function. So what doesn't it like? Okay. So it expected type const found. Just that. So it wants a pointer to the time spec in there. So that means we need to go to our here and do that, right? Yep, that's what we needed. So we needed to pass a pointer to the time spec. Is that what I'm doing? Am I doing pointers anywhere else here? Const. I don't think I'm passing a struct anywhere. So the question is, do you store a pointer in the data, or do you just store this and then in here just do a pointer like that? I'm not sure what the right answer is. I think this is the right answer because the data in the command owns the timestamp, and so it should just have the data, and then here is a reference to it. Would be my take on it, but I don't know if it super matters. The thing you have to be super careful and zig about, because it doesn't catch it, the compiler doesn't catch it, is returning a pointer to something on the stack after it leaves the stack. Then you just get a pointer to a random location on the stack that could have whatever, and then you have random data, and it really throws things off and you have no idea what's going to happen. It's undefined behavior, and the compiler does not automatically catch that. So you have to be very careful not to like instantiate something in a function, then return a pointer out of that function. It's a foot gun for people that aren't used to that, and I've definitely done it a couple times. But that's also because I haven't done a bunch of C lately. So. Because I mean, you can do the same thing in C. So. Okay, so we have, I think, everything wired up. We haven't set any flags, which I think is fine for right now. We're just going to I think we're using a relative timeout here just to begin with. We might want to do an absolute at some point. I know Tiger Beetle in their timeout function uses absolute. But I'm not sure why, but I will look into that later, not right now. So let's try to do this. So I'm gonna head over to our main function. I'm just going to get rid of what we were doing before. So we don't need a socket, we don't need that. Okay, instead of loop.accept, we want, and this is where we add the helper function. Sorry, that's the one thing I forgot. So we don't want to make our callers handle continuations. Like they should have no idea what a continuation is, because that's kind of at a lower level. And then you know what all they need to know is they have a timeout command and they want to or some timeout data, and that's all they care about. They want to pass that in to a function. So like we can look at just accept here, right? So this is like kind of what we want to take it from. At some point I'll go alphabetize all these functions. I just haven't gotten to it. So let's call this timeout. So it takes itself, takes not an address, not that. It does take a pointer to a continuation, and this is something I haven't actually figured out a nice way to handle. We need to allocate, some continuations on the heap somewhere. Not necessarily on the heap, but we need to allocate them somewhere, put them somewhere that is, safe to reference and will last long enough. So right now, I'm just saying, like, hey, give me an address to somewhere I know is safe. That's it for now. We don't need this. We don't need that. So what we want to do instead here is get rid of those things. We want this to be a timeout. Sorry, what was that? Data timeout data, and then we should. I don't like. Oh, loop.x. get rid of some files here. So let me save this. Okay, so we're gonna get a bunch of compilers, so we're done here. Anyways, the one I care about, I guess I don't really care about, I can figure it out. So this is going to be flags equals, I think we're just gonna set the flags to 0 because we don't have any flags, and we want the TS to equal, let's call it time spec. Okay, so Dustin asked, I'm guessing there won't be any continuation data at the pointer address when the timeout helper function is called, just a pointer to a safe address. Correct. Yeah, so if we go look at main, you can see right here I'm setting like basically saying here's 10 continuations, and I'm setting them to undefined, which means it's just whatever is there already. It could be all zeros, but in reality it's just a bunch of random crap. So I mean, you don't know what's there. And then we set the memory to what we want it to be. So we don't have a time spec here, so we want to pass it in. And this is also where we probably want to just do, let me see what we have in just the standard library for time. Probably just a timestamp. We get to 100 times seconds relative to that. It's probably not what we want. We probably want to. Maybe we do want to do just absolute, and then that way we can pass in a timestamp. That might be easier. Milliseconds in seconds. I really don't know what we want here. Okay, so let's just call it a timestamp for now. Which is which is a I-64. So we'll do that right now. So we want a new. We probably need to default or. So we have not an operating system, but a okay, so we have a POSIX time spec, but we're not necessarily, we don't want to do POSIX here because this is ILOOP, so it could be a non-POSIX system like Windows. Do I do POSIX anywhere in here? I hope not. Looks like I do. POSIX sock adder. Oh, I'll have to fix that later. So I guess the question is, how do you make a time spec? The kernel time spec, which is a second and a nanosecond. So I think let's just try passing in seconds here. So let's just call this seconds. It's I-64, is that right? Here, yeah, it's an I-64. Okay, so we're just going to create a time spec in place here. And then, yeah, just set it to seconds. We'll see if that works. And then, so yeah, so this is where it actually sets the data. So it's continuation.init. You can see it takes a pointer here and then sets the actual field, like the task command callback. So it, at this point we have a valid continuation. I need to add some asserts here, but that's a problem for later. So back in our main one, we can do a loop.timeout. Say we want to timeout for 5 seconds. Our continuation is going to be continuations of 0. And our callback is still going to be our dummy function. Yeah. And we want to get rid of this. So it's just going to tick. It's going to tick. It's going to be a hot loop. That's fine. And I'm going to get rid of this ticking so that we don't print out a million of those. And then when it's done, I want to just say that this is the timeout. Otherwise, so in theory, this should now work, and it should sleep for 5 seconds. We'll see if that actually happens. Okay, so it does not like something. Oh, toCommand. I forgot to write the toCommand function, which I need to extract into just the command function, but that gets into some of the comp time stuff I'm not super comfortable with yet. So let me just steal one of these. This is going to be timeout data. CMD like that. So super straightforward, but needed. Okay, still doesn't like something. Okay. Did I? Oh, dot accept. I need to change this to be the right one so that the types actually line up. There we go. Now we watch the world explode in 5 seconds. I hear my CPU fan, and there it went. It worked. That was about 5 seconds. Yep, 5 minutes. Just to be extra sure, if we change this to 3, do it again. Should be 3, and if we do it again, it should be faster because we're not compiling again. Yeah, there we go. So there we go. We have a timeout, and it is relative. I don't know if that's the right choice. Like I said, Tiger Beetle uses an absolute. I'll have to think about that at a later point. But we have the first part of what we want to do done. Yeah, this is on my big desktop. So this is, do I have HTOP? So yeah, so 32 cores, 64 gigs of memory. So it's a beast. 32 logical cores, I should say. I think it's only 16 physical cores. I could be wrong about that. I don't remember. Only, in quotes. All right, so I think this is where I'm going to stop for today, and hopefully tomorrow. Okay, so if you remove done equals true from dummy, but keep the logging, does dummy only get called once? Oh, good question. So I think we're going to just see this is now going to hang forever because we never set Yeah, so it's been more than 3 seconds, so it's definitely not happening again. So if we go over into where is it in here? Let's see, this was count, right? Yeah, so let's just change this to 3 and see what happens. There's our first one. Yeah, it's not doing anymore. So I think you have to explicitly set that flag. This timeout multi-shot flag. I mean, yeah, that's fair too. Once, and I need to do some digging and add some like S-trace, or do like an S-trace on things. There's an IO urine specific way to do it, to see it, to make sure it's not getting called multiple times. But I need to dig into that more. But you are also correct in that, or no, I don't know. So in theory, the what would happen, I mean, we can just go look to where the handle completed is called, right? So I guess this will be here. Where's my tick? Oh, here. This io.tick function. So we copy it, and then self-handle complete, which is just setting the result, and then we set the status to completed. So I mean, we are updating the status to this, so we should never, although I don't think we assert, like, if we assert here that c.status dot waiting, right? Because everything that gets here should be waiting, it should be queued. Let's see if we get an exception or a panic. So no. So I don't think it ever gets it back in, but if we, how do I do this? Let's select, okay. I want, in the flags, data.flags, where are we setting that? Is that in, yeah, flags equal 0. I want to see. I don't know where the flags are defined here, so I can't grab them easily. But I will want to test that. Actually setting that flag and seeing what happens. I wonder if I can tell from the man page. Yeah, it doesn't tell me what the actual flags, like what their values are, so I can't just do the bit shifting myself to do them, or the ORing together. So I'll look into that and see what's up there. Yeah, anyways, what I was getting at is I think that I'm going to call it here today. And the next step for tomorrow is to actually have our event loop just wait for that timeout, so we don't have to do like a hot loop or a sleep or anything. Yeah, that's it. So thank you both for tuning in, and I will catch you all later. Thank you.